topologies of the circuits using the MOSFETs, which is pretty much similar to the BJT device. So we are not going to spend so much time for this, but we just review quickly. So let's start with, again, with the physical structure of the MOSFET. So the MOSFET consists of a semiconductor, an insulator, and then a metal contact on top of the insulator, which basically makes some metal oxide semiconductor capacitor, right? Because you have two plates around two, let's say, conductive plates around a insulator, so it forms a capacitor. And the MOS is coming from the metal oxide semiconductor. So initially we start with this structure, and then let's say we have a p-type semiconductor at this bottom, right? We try to apply some voltage across this capacitor, basically. So with this polarity of the voltage, basically the positive charge will be stored on the top metal, and then a negative charge will be stored at this at the surface of this interface between the insulator and the semiconductor, which is a negative charge. And this charge are the electrons. And then we were thinking, what if we add two more contacts from the sides and apply a voltage? So initially, if you see this material, the p-type, doesn't have that much of conductive free electrons. But once you apply this V1, basically you are trying to catch some free electrons at the interface of the capacitor, and then if you apply some voltage around here, then now this free electron at the interface can conduct. This is the way that the MOSFET device basically works. Initially, the channel, once there is no voltage, the channel basically is between the two contacts of the here is depleted from the free charges. And once you apply this VG basically from the gate, you are basically absorbing some electrons underneath of this surface. And then this free electrons now can connect the two sides of the device, right? The channel forms. So we were talking yesterday that how this current may change based on the thickness of the dielectric or the length of the channel. So we told that if you increase the dielectric thickness, basically the effective capacitance over here will be reduced, so that with a given voltage, basically to the gate, the thicker oxide basically has less capacitance, so less charge will be stored, right? So once the less charge is stored here, means that the conductivity is not too high, right? On the other hand, if you have a thinner uh, isolator, once you apply the same voltage to the gate, basically, let's say 1 volt here versus 1 volt here, then this capacitance is higher, so it can store more charge underneath. And then since you have more free electrons, so the thinner oxide actually can conduct better. Or if you change the distance between the two conductors, or between the two contacts, let's say L1, and you have another device which has L2, the length of the channel L1 is longer than L2. Then, though the density of the charge are similar between the two things because we are assuming the same thickness for the dielectric, but since the L1 is longer, basically it looks like you have more basically resistance in series from one part to the other part. So we expect that the longer L basically has less current, right? Because the resistance is a little bit larger than the other one. So from these things, we can predict how the device current characteristic will behave. On the other hand, the device is like 3D, right? So we were talking about the length between these two contacts, but it has also some widths, right, at this direction. The width is nothing but just um, like you are paralleling different devices, right? So you can think that you are paralleling different devices, right? So basically, once you parallel several devices, or let's say for the resistor, if you have one resistor and you are trying to parallel more of them, so basically with a given voltage, you basically have more current, right? So it just scales the current of the device, right? So if you increase that width, basically it looks like you are increasing the total number of the transistors and the current will be increased, right? So here is showing that basically, first of all, you are applying some gate voltage over here, and let's say this part of the contact is grounded, and then you try to pass some current through your device from the drain, and then this shadow thing is showing actually the charge density that is underneath of the channel. So since the VD is higher than the other side, basically the charge density at this region is higher and up to here is less. So, but this profile of the charge density finally makes the final current characteristic of the device. So if you increase this VD too much, so this charge density will be less, and finally there is some position that it kind of like make it depletion region. So we called it the channel is pinched off. So the channel is pinched off. So after a certain value for the VD, in fact, the channel start pinched off, and then it seems that there is no way to increase the current. So here is showing that how we drive the current versus voltage equation for this kind of device. So basically, what is important for us starts from here. So basically, let's say we have a MOSFET device, we show it like this. This is an N channel. So as you see, we are showing that there is a gap between the gates to the channel in the symbol, right? It looks like a capacitor. And here is the drain. The other side is the source. And here is the gate. And then the ID, the drain current, versus the VGS, which is the gate voltage. And it shows the dependence on also on the VDS, the drain source voltage. So in fact, there is another term here in the MOSFETs, which is called V threshold. This is the starting point for the MOSFET to conduct. So before reaching to this threshold voltage, the device is totally off. And after VGS reach to V threshold, then still it start conducting basically. And as you see here, there are some factors that is related to the physical size of the device. So this Cox basically is telling that how much is the oxide, that insulator part, how much is the density of the cap between the channel and the gate. If you remember, there was isolator here, insulator here, right? So basically we can control the thickness of this insulator to change the cap density. So it's a physical, uh, it depends on the physical and the thickness of this oxide, right? So this is something that the process given, that the process designer is controlling. The mu n basically is the mobility of the electrons in the semiconductor for the NMOS or N-channel device. And then L basically is the length of the channel, right? So basically you have these contact points from the drain and source, and then you have this insulator, and then you have this gate contact here, right? And then the L actually is how far these two contacts are from each other. So this is the L, and then as we mentioned, if the L is longer, so it looks like the path is more, the resistance of the path from one contact to the other contact is longer. So you should reduce basically the current, right? It is in the denominator. And then the width is basically like how big the device is from the other side of the perspective, right? So the larger the width means that you have kind of paralleling more of these small tiny transistors, and the current will be scaled based on the width. So this current characteristic depends on the VGS and also the VDS, and is defined for the, let's say, the triode region of the device. This is before the pinch off happening. We call it in the triode. The current model is like this. So if you plot basically that equation, the ID versus the VDS, and you assume that you have some given value for the VGS, then if you plot versus VDS, you are seeing that initially if the VDS is 0, so there is no current, but if you increase it, start increasing and reach to a maximum, and then it suppose go back based on that equation. But we know that this region is not happening. The pinch off happens, and then once the pinch off happens, basically this will remains like constant practically. So this region, which is the pinch off in for the MOSFET, we called it like saturation region basically, because the current curve is saturated, right? The current curve is saturated to a constant value. And then basically this is the active region that we use the device for the as the amplifier. And one thing else is good to remember is that this active region actually happening once the VDS is larger than VGS minus V threshold. So if we want to compare it with the BJT device, actually BJT also showing kind of similar curves, right? From the collector to the collector current versus the collector emitter is pretty much similar. And we call this flat region like active region. And then this part that the device was at the saturation, we a little bit confusing, but for the BJT, this area we call it saturation. And then this turn on voltage after the saturation was something always fixed around like 0.2 volt, right? So it was kind of the fixed value, but for the MOSFET is a little bit different. It depends also on the VGS of the device. and it has to be larger than the VGS minus V threshold. So the saturation current basically is given by this formula, which is not anymore depends on the VDS after the saturation for the MOSFET. And then the device will be like the current source. So basically here is trying to show the different drain current versus VDS for different value of the VGS. So the lower the VGS minus V threshold means the lower current, right? It it comes up to a maximum value and then will be like flat. It will be like a current source after the pinch off happens. For the higher VGS minus V threshold, the higher drain current, like this, right? So what we are seeing here, basically the ID max, which is the transistor maximum current at these curves, are depends with the VGS minus V threshold square. So basically we call this ID is like a square law, the dependence between the ID and the VGS. But for the BJT, if you remember, basically the collector current was like IS exponential or exp of a VBE over VT. So if you compare these two, the drain current is like a square law, right? But the collector current is exponential. So basically the collector current is from one perspective is much more nonlinear than the drain current of the MOSFET, because drain current also nonlinear because of this square, right? But the still is just only single polynomial with the second order, but the collector current basically is exponential. So the exponential has some, if you want to expand it as a series, is having all of the contents. If you want to just expand it, it has some more, all of the contents to the more orders. Some VB to the n, right? And some coefficients for this Taylor series, right? So basically, collector current is more nonlinear in terms of the linearity rather than the drain current. So on the other hand, at this low VDS region, basically, at the low VDS region, we can tell that this ID VDS curve are a little bit constant, and this constant lines at the low VDS basically it looks like a very similar to a characteristic of a simple resistor, which we called it the R on of the device, means when the device is on, how much resistance it has, R on. And this R on value can be controlled with the VGS. So the higher VGS you applied, you make the channel more conductive, and then the resistance will be less, right? The resistance is less because this is basically ID versus VDS. And this one, the resistance is higher. And based on the initial equation, actually you can calculate this R on value according to this equation at the small VDS. So based on this, we can actually make some variable resistors if needed to tune some of the circuits, right? You can control, you can put this device as a resistor and control the value by adjusting the voltage of the gate source. So here is the summary so far. So basically the device has two regions. So at the low VDS, it will be like more like a resistor at this corner, and the resistance value was given by this formula over there, right? This formula depends on the size of the device, you can adjust it, and based on the voltage, you can control the resistance value. And then if the VDS is larger than VGS minus VT, actually the device go to the pinch off region. As you see, the current, the charge density at this region starts pinched, and then the current will be constant, which we call it saturation region for the MOSFET. So, so as a rule of thumb, in order to really understand which region the device is after you bias your device, you only need to check whether the gate voltage is larger than the drain plus one V threshold, basically. The way that you simply um, check whether the device is in the saturation region or the triode region is that the gate for the saturation basically has to be less than the drain voltage minus one V threshold. So in that case, if the VG is less than VD minus V threshold, means that the device definitely is in this saturation region. Otherwise, we are working at this region. So here is giving some example we want to see, but just skip at the moment. So again, similar to the, if you remember, similar to the BJT, actually, we also suppose initially having a very constant current for the collector, but at the end we will come up with a little bit change of the current of the collector for the BJT as well, once we were increasing the collector emitter voltage. And that were because of the early effect, but here is actually another effect which we'll call it channel length modulation. So in fact, the thing that is happening is that once you go to the pinch off region, means that the charge density at the drain is start just disconnected, right? If you increase the VDS, this depletion region of this charge area will be will be larger. The gap underneath will be larger. So basically, you have these contact points, and then the charge density to the drain start pinched. And then if you increase the drain voltage more, then you will come up with that the charge will be even, the charge density will be like more like this, and this pinched region is longer. So in fact, the effective length of the device is changing. The effective length is now this much because only we have this area is just the charge is underneath, the other one is not. So the length of the device is changed based on the drain voltage. That's why we call it the channel length modulation. So the length will be changed and modulated, the effective length basically, based on the drain voltage. And once this happens, means that basically it looks like that this L is changing, right? So with the higher voltage, basically this L will be reduced. So the total current will increase. So in order to actually model it using equations, we are not going to change this L like over here, but we just show it based on another factor that shows that this current is depends on the VDS. And this factor basically we define some parameter like lambda to show how much this VDS variation is going on. So so after we know the characteristic of the DC characteristic of the device, basically we can define all of the other components that we were defining for the BJTs for the small signal, like the GM, especially like GM is important. And the GM is basically what? The GM is saying that how much current of the device changes the ID once you are changing the input voltage, VGS. So for the BJT, if you remember, the GM was how much collector current is changing once you are changing the VBE. So in order to calculate the GM for the BJT, we needed to take the derivation of this IS exponential equation respective to the VBE, right? So we basically were calculating the differentiation of the IC to the VBE, right? This is what we need. We want to know how much current change once the VBE changes, which will be which was actually the IC value, the DC of the device divided by VT. The VT was the constant 25 millivolt voltage. So again, for this device, we need to do the same thing. So we have the equation between ID and the VGS once the device is at the saturate point. So 1 over 2 mu n Cox W per L. And then this is the equation of the drain current. And then you need to take the derivation of this ID versus the VGS. So dID over the VGS, dVGS would be mu n Cox W per L times VGS minus V threshold. So sometimes we just show this VGS minus V threshold as V over drive. This is a notation. It says how much we are having over driving the gate voltage over the V threshold basically. So what we have for the GM basically is this equation. And then you can rewrite that equation basically with different formats. So the initial format was this, which we had derived, right? But on the other hand, you can rearrange these terms to show the GM versus the ID, basically. This is a little bit similar to what we had for the GM, for the BJT, because with the BJT, we just needed to know the IC and then the VT. So here we want to know the GM based on the drain current. Or there is another formula for this that is depending on both ID and the VGS. So either of these things can be used to calculate basically the GM. So we have different cases to compare the GM. Like we can assume that the GM, the W per L is a constant for a device, and then we have the option to change the VGS minus VT as the input. So we can basically control the GM by, the GM is proportional to square root of the ID, or GM is proportional to the VGS minus VT. Basically, you need to refer to the equations. So this comes from this equation. It says that if you change the VGS minus V threshold, basically the GM proportionally changes. But this one is coming from this equation, which we are seeing that the GM actually changes with the square root of the ID. So in order to increase the GM, basically we need to, let's say, in order to double the GM, we need to uh, increase the ID 4 times, right? Because it's square root. But for the BJT, if you remember, the GM was like this. So if you increase the current 2 times, the GM will be 2 times. So in terms of the GM, the BJT device has a better or a higher GM versus the current, because the GM is important parameter for us, right? GM is showing up in the gain, right? So the higher the GM is, the higher the gain. So on the other hand, if we calculate the or if we assume that this W over L is under our control, we can change the size of the device, but we want to keep this VGS minus V threshold constant. Then we will come up with this. So basically what we are seeing here, if you increase W per L and the VGS minus V threshold is constant, then the GM will be proportionally increased, right? So we can define different configs at different situations and figure out which parameter we need to change to adjust the GM value that we need to achieve. So here's a little bit more detail. So one other thing that this MOSFET device basically has is, so basically you had this three terminal, right? We were showing initially, but in fact the substrate itself has some connection and needed to be biased. The substrate basically is p-type for the n channel, and then we have some contact point to bias the substrate to make sure that it's not float. And then in order to this device to work, basically we always need that this NP junctions, basically, because here also P, right? The substrate is P, and then this junction of the channel is N, so they have to be reverse biased. This diode, basically, there is a diode here to the channel, right? So this diode always has to be reverse biased because here is P, right? And then we try to bias this P substrate to always be less than the voltage of the drain and source. So usually it has to be connected to a lowest voltage for the N channel in the circuit. And it can be even negative. So if you change this is the way we show it. We show some center line showing the bias of the substrate. If you change this voltage of the substrate, basically respective to the source, it may change that V threshold voltage. It's some functions that depends on the semiconductor work function or something like that. So this sometimes will be used to adjust the V threshold of the device. So again, similar to what had seen for the BJT, we can model this device like the large signal or small signal and other ways, right? So basically, I'm just trying to show this the symbol. So we have gate, we have the drain, and we have the source. So we are trying to model it like with some model of the device. So first of all, we know that there is no connection between the gate to either source or drain because there was insulator between, right? So here is like open. But on the other hand, we know that the current of the drain to the source, if the device is at the saturation, which is showing that VDS is larger than VGS minus VT, would be like this. So it looked like a current source, basically, almost constant if you ignore this part, right? And then the equation will change if we go to the triode region, and the equation at the triode is like this. And if you go very low VDS, then we told that the model between the channel can be like some constant resistance, which will the value can be changed by adjusting the VGS minus V threshold, right? These are some models that we can define. And on the other hand, we can actually define the small signal model again, which was based on the GM, which we already see how it is. And then again, similar to the BJT, it can show up some limited R out, right? And then the limited R out can be calculated based on this equation. So if you remember for the BJT, the R out was basically V early divided by the collector current. In that sense, they are kind of similar because if you increase the DC bias, the R out will be reduced. And also in here, if you increase the drain current, also the R out will reduce. So it doesn't need to repeat everything for the PMOS, just we know that the source of the channel over the PMOS is the P channel, means that the holes are conducting basically in this substrate, and the substrate is N-type. Okay. So everything for the PMOS is similar, except that the source, the polarity of the voltage and the current changes. And then in the equation, basically, in terms of mobility of the electron, we use the mobility of holes, right? The other factors are pretty much similar. The threshold voltage, the sign will be changed because everything is just a negative polarity, and nothing is different in terms of the small signal model for the PMOS comparing to the NMOS. So again, similar to BJT, actually, the PNP and NPN, both of the device were showing the perfectly similar small signal model. So here it's showing how people actually made the transistor in the CMOS technology. CMOS means complementary MOS technology. Complementary means we have both type of the NMOS and PMOS together on the same wafer, but once you are manufacturing the devices. So basically what you have is a P-type substrate initially, and since it is P-sub, then you can build the NMOS device on top of it, right? Because the NMOS needed a P-sub. But for the PMOS, basically you need to have a N substrate or N body. We call this like body, and then you need to first make part of it like an N. We call it N well, means that the doping will be changed to the N, so that we can actually make this PMOS structure, because PMOS needs the N as this body, and then the holes should conduct over here like this. So let's compare the bipolar and the MOSFET transistor quickly. So as you saw, the MOSFET, the current was quadratic, but for the bipolar is actually exponential. So for the bipolar, we call the device is active region once the collector base voltage is larger than 0. We call it active, basically, but in MOSFET, we call it saturation. Just the naming you can tell so far. Once the VDS is larger than the VGS minus V threshold. And then once the VDS is lower than some value or less than VGS minus V threshold, we call it the device in triode. But on the other hand, for the bipolar, we call it in saturation. So this naming, you need to be careful, not be confused by. So what else we have is there is some base current for the BJT, right? The base current was initially like the base current is IB is what is collector current divided by beta. So it has some base current, though is less than the collector, right? But for the MOSFET, actually there is zero current, right? From the input side is zero because there is insulator. So in the BJT, we have the early effect that's showing up as the output impedance. At the MOSFET also have some effect that calls channel length modulation that change the that show up as a limited output impedance. And here is describing how the current basically are conducting inside the channel. Basically, here is the drift, and then for the bipolar, basically is the diffusion. And for the MOSFET, we can define some region that is voltage dependent resistor, but we don't have that region basically at the bipolar device. So studying this, actually, we need to actually go for the seeing how this MOSFET device is used at the circuit level. So the MOSFET is using pretty much similar to the BJT in the circuits, but they have a little bit different in terms of calculation for the bias because the equations are different. The equation for the MOSFET is, if you remember, at the saturation is 1 over 2 mu n Cox. You need always remember this VGS minus V threshold. So for a given transistor, basically, you need to know mu n times Cox, basically. Let's say W and L are the size of the device. You can adjust it by yourself as a designer. And then this V threshold also is a process or manufacturing parameter, so is already given to you. And then you adjust, let's say, all of the values so that you can come up with certain drain current. And once you get the drain current that you want, then you actually can calculate all of the GM and other things, right? So here is just showing different schemes for the bias. I'm not going to describe it that much. And just review it because it's pretty much similar to what we had for the BJT. So for example, here it's showing basically a common source, which is very similar to the common emitter, right? So if you plot the small signal model, actually is even simpler than the BJT, because for the BJT you had some RPi over here, but here now the RPi is open, right? Because there is no connection between the gate, right? So in fact, the RPi is, you can say, infinity, or on the other hand, you can tell that the beta for this device is actually infinity if you want to compare with whatever you know from the BJT. So the gain is similar to that, right? AB is just GM times the load impedance. But the GM you need to calculate based on some of the equations. Depends on whatever you have available. If you have the drain current and you know W per L and the other values, then you use this as the GM. There are different formula for the GM to calculate. Depends on whatever you have in hand. And then for this, actually, it is much easier because this input impedance or R in of the device is basically easily infinity, right? So here is checking that if the device is in saturation or not. And then again, Here is showing the input impedance infinity, right? The R out is the RL, it's similar to whatever we knew. And then if you include the limited impedance of the drain, then you can actually make it a little bit more accurate for the R out, but still the input is infinity, right? And here is showing how the gain changes once you are changing the length of the device, basically, assuming you are biasing the circuit by a current source, and basically there is no RL, and then the RL is only the R out of the device. So here is showing how it changes. Actually, one thing you need to remember or know is that, so if you remember, the RO value was basically uh, 1 over lambda ID, means the higher drain basically reduce this R out impedance. So if you try to increase the current of the device, basically these are also reduced. And if you remember, the gain was GM times R out in this case, right? Because there is no other RL in parallel, so it would be just R out. This is the maximum intrinsic gain of the device. But if you increase the current, this RO will be reduced by a, so the RO will be reduced by a factor of ID. On the other hand, GM will increase, but the GM will increase by a factor of square root of ID. So overall, for these devices, you see that the gain basically drops once you increase the ID. This is one thing you need to know. And on the other hand, this lambda is a given number, but the lambda also depends on the L, uh, the length of the device, is inversely actually. So if you increase the length of the device, this channel length modulation factor will be less basically. So if you increase the device length, basically you are basically reducing the lambda factor so that you are increasing the R out. So that's why here is showing that once you are changing the L, the overall gain may increase with the constant drain current, because this R out is basically, or this lambda is changing and this R out is increasing. So here is just giving some example. Let's say we are trying to get the highest gain. We put the current source here so that we do not load actually this node with extra resistors, the output node, because we want to increase the GM RL to the maximum, right? We need to increase the RL to the max. So we will, in fact, we can make this current source with another device, basically, right? If you remember, the device itself is acting like a resistor, like a current source, if biased properly. So here it is showing that they use some PMOS here to make this current source. And if you want to actually calculate the gain for this case, you need to just put the small signal model for each device, right? So for the small signal of the top device, basically this VDD need to be shorted, this V bias is shorted, so the small signal would be like this, basically. And then since the VGS of the top device is 0, so basically this current source basically is not there, right? And whatever left is just only RO2 from the top device, which is considered like a big resistor. So after doing that, then the whole gain for the bottom device, which is a common source, is just GM RO1 in parallel with RO2. This is kind of the highest gain possible to reach from this device at the current common source, right? So, so on the other hand, we can actually put another device like this, but since we are actually having some source, we are looking at the source. If you remember for the BJT, once we were looking from the emitter, actually the impedances we're seeing was R pi divided by 1 plus beta, which was roughly 1 over GM. This is pretty much similar once you are looking at to the source of the M2. Basically, what you are seeing is 1 over GM is showing over here. And the 1 over GM is considered not a big impedance if you remember. And then if you want to be more accurate, you put this RO of the device in parallel, but in fact, 1 over GM is dominant. And then you can calculate the gain of this structure, which will be GM times the load, but the load is basically 1 over GM2. And here is more simplified because the drain currents are same in this case, right? The drain of the M2 and M1 have the same current, so it only will left the ratio of the device size basically is making the showing that how much gain this device has, this config has. So here is the same thing, but just the input device is the PMOS, and then the load basically is the NMOS. Another PMOS actually. This is the another PMOS looking at the source. So the load is 1 over GM1, the impedance. And then the common source device is the top one, just the PMOS. So basically what we have is the GM2 as the device, input device times the impedance, GM1. And then if you become too much accurate, then each of these devices has its own R out to the ground, right? So they are in parallel. So again, similar to the BJT, we can assume that there is some source resistor at the input, right? It's pretty much similar. Then we can again calculate everything for this. So if you remember for the BJT, once we put this RS, in fact, the input impedance also increased, right? If it was BJT, it was like RS plus 1 plus beta plus R pi. But in here, since there is no conduction path from the input, basically the input impedance is highest. On the other hand, if you remember, we could actually move everything from the base to the emitter for the BJT. So you can basically do that here. So if you move to the emitter, basically what you were seeing is pretty much similar to the BJT. There is 1 over GM resistor, and then you had this RS, and then the V in kind of applied over here at the source. And then you can calculate this source current basically from this equation. So the source current, I source, is basically the input voltage divided by the series of two resistors, G1 over GM plus RS. And then the IS is exactly ID in the MOSFET because there is no other path the current go. There is only single channel from drain to source, right? So you basically know the ID, and if you multiply the ID by the drain resistance, it gives you basically the output voltage. So the total gain would be with a negative sign again, the RD divided by 1 plus GM plus RS. So we don't need to memorize this thing. It's pretty much similar to the BJT. So again, here is showing that, let's say this resistor is just another transistor at the source, so you need to just model the resistance value from the device and then solve it. So one more, uh, the other way is we assume that there is RG, but this RG doesn't do anything for the MOSFET because there is no current passing through the gate. Basically, the V in is just over here, right? Since the impedance is high. And then again, we can calculate the R out of the device in presence of the RS is almost pretty much similar to whatever we had before. If you remember, for the BJT was, we were showing it like 1 plus GM RE times RO, if I am correct. So this is pretty much similar actually. So if you simplify it, it's pretty much similar. So in that case, the calculation is similar. I guess for the BJT, it was 1 plus GM, basically RE in parallel with R pi, if I remember correctly, times R out. In fact, you can use the same thing, but since the R pi here for the MOSFET basically is infinity, right? Then this will be simplified to this. You can. So again, nothing new. Nothing new. I'm not going to spend more time on it. So we would be able to, again, similar to whatever we had seen before, we need to have some DC block for the bias at the input. And if we don't have this bypass capacitor, it is not working well for the gain. So you add this bypass capacitor to increase the gain. Something similar to whatever we had. So again, similar to the BJT, we have the other type of the gain, like common gate. There was common base, right? So again, the gain is similar to what we had, but the input impedance is a little bit different, right? Is looking at the source. So once you are looking at the emitter or source, the input impedance you are seeing is 1 over GM. So again, it's similar, right? So we don't need to talk about it more. And again, similar to that, we can add some source resistance. Now, since we have this 1 over GM as the input impedance, then we need to consider this voltage divider at the input. It's pretty much similar to the BJT, and then you can calculate it easily. And moreover is, yeah, everything is similar. So this gate resistor basically to the for the MOSFET doesn't do anything since the device is already high impedance, no matter there is no current, so no matter you have this resistor here. So here just showing one example that how the common gate is biased. So basically it's biased with these two resistors plus the R3, similar to the BJT. And then we have this cap to isolate the DC from the input to this node. And then whatever left, you need to just calculate the gain, which is not that big deal here, is okay. And then we have this other type of the config, which is the source follower stage. So the source follower or the common drain is again similar to the emitter follower or common collector. So you apply the voltage to the gate and get the output from the emitter. So this device from the input is always the input impedance is high. So in that sense, it's very good for the voltage amplifiers, right? If you remember for the BJT, we had the problem with the limited input impedance, but this device for the MOSFET, it doesn't have that problem. But on the other hand, we still need to have the output impedance to be lower for the voltage amplifiers. So if you use this kind of common collector or common drain for the MOSFET, then the output impedance will be less because what you are seeing from the source is low, right? Is a 1 over GM impedance. But on the other hand, the gain is not high, so it is good for as a buffer at the output stage to be used, right? We don't need this buffer at the input for the MOSFETs because the MOSFET already any config that the input is the gate, already the input impedance is high. But for the output, it is good to have this kind of buffer to reduce the output impedance. And the gain is how much? The gain, basically, you can, similar to the BJT, you can move the V in from the gate to the source or from the base, if you remember, to the emitter. So what we do that was moving the V into the source. So from the source, we have this 1 over GM. If we go there, and then we have this RL, and here is the V out. Then you can calculate basically V in, V out over V in, right? So what we left is RL divided by RL plus 1 over GM, which is roughly close to 1, is less than 1 usually, right? Because we still have something more at the denominator. Okay, so here are some examples. We are showing the source follower with biasing. And then just different config and different loads. All of the loads are based on the transistor. So if you want to solve it, you need to just model it with the correct small signal model. So, so I want to give this as a practice for you. Let's say we want to find the gain, how we can calculate the gain from the V in this config to the V out. Let's try to find the gain for this structure, for example. Let's assume that the M1 has ID1. For example, everything is unique for each one, like GM1, ID1, and the M2 is ID2 and GM2. So how we can calculate the gain? Okay, so as you saw here, actually, we need to make the small signal model first, right? How we draw the small signal for this? We open up the current source, we short circuit the voltage source and DC source, right? Because they are not varying. And then the model will be like this, right? You have this M1 device, here is ground, and this source is attached to the source of the other device. Here is ground, right? And here the drain is connected to the load RD, and here is the output, the out. And here is the input, right? So what we are seeing from the input side, basically this transistor is like a source follower, right? Because the input is the gate, the drain is ground, and then the signal comes out of the source, right? But how we can calculate the from V in to Vx, let's say this node is the Vx, basically is the current source, so source follower, and then we need to know the impedance thing from this side to calculate it, right? The impedance thing from the source of the M2 basically is like a common gate device, right? Because the input is at the source, the gate is grounded, and the output is at the drain. So it looks like a common gate device. So since we are looking at the the source, basically, the impedance basically is what 1 over GM, 1 over GM2, basically, right? The impedance seen from this. So if we want to solve the gain from V into Vx, basically we can move it like a common drain, move the V into the source first, like we can assume that there is V in, and then we have the 1 over GM1 as the source resistance of the device 1, and then we actually we are seeing that the impedance at the source of M2 is like 1 over GM2, right? So here would be the Vx, right? So the Vx over V in basically will be just this 2 voltage divider, which is 1 over GM2 divided by 1 over GM2 plus 1 over GM1, right? And then you can tell from here we have the common gate that Vx is input and the V out is the output, right? So the other gain we need to calculate is V out to Vx basically, which is the common gate, which would be GM2 times RD. GM2 times RD. So the overall gain is actually just the multiplication of the cascade of these two gains, right? Which eventually you will get this value, right? So this is the way we just simplify the circuits from each part to each part and move on. So how about for this? It's pretty much similar, right? First of all, actually this circuit has two outputs. One is as the common. So the output one is like from the input to output one is the circuit is like the common drain because the input is gate and the output is the source. But on the other hand, from the input to the V out two, basically it's like the common source. So it doesn't matter, you just replace each of these dummy devices underneath as a load resistor. So this should be something like 1 over GM2, right? Because we are looking at this device as a source. So the impedance we are expecting is 1 over GM2. For the M3, again, we are looking at the source of the device, so the impedance is also low, like 1 over GM3, depending on the current of it and the GM value, right? So how about for the M4? For the M4, basically the small signal model here is ground, here is ground. So this device, the gate and source are grounded. And then the drain is what we are looking at the drain. So basically what we left is just the R out of the device, RO4. And then it's nothing, just some resistors and the common gate or common and the common emitter or common drain. So I guess this is enough for the MOSFET, but you need to do more practice to figure out the biasing, calculating the GM values and the device sizes a little bit different than the BJT, because in the BJT, whatever you need to know was only the collector current, right? But in here, the size of the device is come into the effect, basically W per L, that in addition to actually the drain current. All of these things together can give you the GM and the R out and all of the things. So it needs the little bit more initial calculation actually to find the GM and the bias points. But after that, they are pretty much similar. So from this part, in fact, we are going to solve some actually very useful component in electronic. We call it operational amplifier. But at the beginning of this section, we are seeing the circuit. I mean, this operational amplifier as a black box. We are not going to describe at the beginning what is inside at this chapter, but we are considering how this device is defined and what characteristic it has to have, basically. So I guess we can start this section maybe on the next day of the class, because it's a new topic, maybe better to start it a little bit more fresh. So if you don't have any question at this moment, we can close this session for now. So any of you guys online attendance can have any question? Ravan, Moayyad, Mohammed, any of you, do you have any
No,
question?
Doctor. Thank you so much.
So we will resume the next chapter, maybe actually depends on whether we're supposed to having an exam for the signal and control on Sunday. So do you have any feedback on the exam? Does it work for you to have the exam on Sunday, or do you want to attend it, or I don't know how is your situations. Do you have any
Maybe it's
comment?
better to do a poll in the group, I think.
It's better to do what? Sorry.
A poll, like the student can choose whether
Sure.
they
So how
Sunday
about
or.
yourself? What is for yourself?
I have a summer semester, so I have a
Yeah.
midterm in Sunday. But if the all students are good in Sunday, I can take it. But maybe some students are not good in Sunday.
So for you, is which day is better?
I think maybe Monday or any day else it's be better
Okay.
because I have midterm in Sunday and midterm in Wednesday.
Okay, understood. And so I guess we this time we have the exam at the Sultan Qaboos University.
Okay, that's good.
Yes, because the one of the student or some of your the students cannot attend at the late time, cannot go out of campus. So
Oh,
they're
okay.
so maybe this time we just have the exam inside the Sultan Qaboos at a certain location that we have these classes, this lecture
Okay.
theater room, I guess.
Okay, that's good.
Okay, okay. Yes, maybe I send out uh, some poll to check. Yeah, okay, no problem. Any other
Okay, thank
things
you,
that you
Doctor.
want? Any questions from the course or anything else?
I don't have.
No, doctor, thank you.
Okay, thank you so much for attending. Okay, see you then maybe next week. Have a good weekend. Bye bye.